leak in our roof. I was waiting for the roofer who never turned up. And then, of course, once you come here, we have this magical bank of elevators which keeps bouncing up above. So anyway, we're going to continue where we left off, talking about training neural networks. A quick recap. What we've seen so far is that the multi-layer perceptron can, Brian, make sure that you can, if you, right? Yeah. A multi-layer perceptron can represent any function. So we can construct it to represent pretty much any odd function that we want. It could be Boolean, it could be a real valued function, it could be a classifier. And the way we would do this is if you had a function g of x, where x was the input, then you would want to construct your network, which is basically a function of its weights, such that the input-output relationship of the network gives you exactly this function. And in order to do that, we defined a differentiable divergence function between the output of the network and the function that you actually want to estimate. You computed the expected value of this divergence over the entire input space. And we estimate the weights or compute the weights of this network to minimize this expected divergence. We also saw that in reality, we don't really have the complete function g of x. So what we do have are samples drawn from g of x. So we have a bunch of samples of x. We have the corresponding values of g. So we have input-output pairs. And from these input-output pairs, where the output is actually the function plus possibly some noise, from these input-output pairs, we must estimate the function. And if your samples are properly drawn, then these x's come from the natural distribution of the data. And we also saw that as drawing such samples is just the act of collecting training data. Yes?
So this is a question that is just related to slides. Are there slides, will the slides be available before class?
Before class?
Just on the website to be able to take notes off of?
OK, I can put them up. I mean, one of the reasons we don't actually put up slides is even now, we have 300 students registered. I don't think more than 100 students are actually watching the videos or the lectures, right? Most students assume that they can just go there, flip through the slides, answer the quizzes, do the homeworks, and get a grade. And in last semester, the policy we used was that we didn't put the slides up. And we had questions from the lecture. And after the quiz, we put the slides up. It's kind of forcing you guys to watch the lecture. And this is the only way I have of enforcing that you actually watch the lecture, because you end up wasting our time asking all kinds of absurd questions on Piazza where the answer is in the lecture, right? And all right. So getting back to this business, we cannot actually compute the expected divergence. And the funny thing is, just getting back to your business about the slides, the statement that I've just made, that you're wasting my time and my TA's time by asking questions, the answers to which are in the lecture, will not be heard by 200 students because they wouldn't have watched this lecture. Right? It's that bad. And anyway, so what we really do is compute the average divergence over all of our training samples. This is our empirical expected error or empirical risk. And what we actually do is to minimize this empirical risk in order to estimate this function. So the overall setup was given a collection of input-output pairs. We compute the empirical average of the error on the entire training data and estimate the weights to minimize this. So here's the overall problem statement. This is a problem of function minimization, an instance of optimization. This is where we left off in the last class. So before I continue with how we are actually going to do this, how we are going to optimize the network, we'll spend about half an hour, which we should have done last class, on what it means to optimize functions. But even before that, the very first thing we have to define is the notion of a derivative. Does somebody want to take a Pulkit, there you are. You have had questions. How would you define a derivative? The slope at a point. Does anybody have a better definition of a derivative? Something even more basic?
change in y.
Yes, go ahead.
Change in y by a infinitesimal change in x.
Perfect, right? So the way we define a derivative is given a function, any function x, and why we're going to be using this definition instead of yours, it will become apparent in a few minutes. So if I have any function, this is f of x, y equals f of x, and this is x, and if I'm at any point x currently, the question I would like to ask is how much, let me choose a better spot here, right? So if I'm currently over here, the question I would ask is how much would a small change delta x from my current location affect the value of the function? What kind of change would it cause in the value of the function itself? So this is x, this is y. If I move x by this much, then how much does y change by? This is the relationship that we are that we are interested in. And the reason we are interested in this relation is that we need, the whole business of optimization, as we discussed in the last class, deals with how much do small changes in parameters and inputs affect the output. So this is what we really need to know. And the way we define it, this is the correct way to define a derivative. Pretty much every other definition is either a shortcut or just wrong. So here, delta x is the change in input, delta y is the change in output. And if you look close enough at a function, eventually for a continuous function, for a smooth function, you will be able to, the function ends up looking planar or linear if you're looking within a very small perturbation of the current location. So the relationship between the change in the output and the change in the input for a small enough perturbation is going to be linear. And so the question we ask us is, what is the scaling constant by which I must multiply the change in the input to compute the change in the output? This is our notion of a derivative. That scaling constant is a derivative. This definition is generic. It has nothing to do with whether the function is a scalar, the function is a vector. No. In the case of a scalar function of a scalar variable, x is a scalar, delta x is going to be a scalar, y is also going to be a scalar. So alpha, we will often represent this as, so for small enough perturbations, we represent that as dx and dy. So the scaling constant is represented using a shortcut as dy over dx. That's a very hokey representation, which causes a lot of confusion when you begin dealing with multivariate functions. But for scalar functions, it's perfectly fine. But a more reasonable way of representing it is just saying f prime of x, which is where f of x is the relationship between y and x, right? Now this is for scalar functions of scalar variables. What happens when I have a scalar function of a vector variable? So here I have y, which is a function of a vector x. And assume for now that my vector x is a column vector. So in the lecture, I will keep assuming that the vectors are column vectors. In your code, it's up to you. You have to transpose everything to make everything consistent. So if this x now represents a vector, what would dx be? Dx is also, or a delta x is also going to be a vector, correct? Delta of x is going to be a small perturbation in every direction. So delta x is going to have the form delta x1, delta x2, all the way to delta xn. Right? And now, the way we define the derivative remains exactly the same. Here's delta y, here's delta x. The derivative in this case is the constant by which you multiply the small perturbation in x to get the resulting perturbation in y. Now here there's a business of convention. And so I'm going to use a slightly different convention than you guys might be used to. I could write this, once I begin dealing with vectors and matrices, I can write this as alpha transpose or alpha, and they end up giving you different kinds of conventions. I'm using the same convention that I used for scalars. So delta y is alpha times delta x. Now, this is a scalar function of a vector variable. So is delta y going to be scalar or vector? Scalar. So what will alpha be? Alpha is going to be a vector. So if delta x is a row vector, what's alpha going to be? Or delta x is a column vector, what's alpha going to be? It's going to be a row vector. Correct? So that means alpha is going to be of this kind. Alpha 1 through alpha n. And the overall computation that you get for computing the derivative is delta y is alpha 1 times delta x1 plus alpha 2 times delta x2 and so on. Right? And what is alpha 1? Any specific alpha. Now, we haven't specified what these perturbations are. So I could set all of these perturbations to 0. And that relationship must still hold. Correct? And so therefore, that is this any particular alpha I is the change in output when only that component is changed and everything else is kept fixed, because everything else is 0. And so that is what we will call the partial derivative of the function with respect to xi. And that we will represent using this dou notation. So delta y is going to be the partial derivative of y with respect to x1 times delta x1 plus the partial derivative with respect to x2 times delta x2 and so on. But where this comes from becomes clear if you start from this one. And now what is the derivative of y with respect to x? Anyone? Jing, what would the derivative of y with respect to x be here? You. Yes? That's just the vector alpha. It's just the vector of the partial derivatives. Yeah? And so I can write delta y equals, what we will generally write this, that alpha is going to be represented using this funny inverted triangle symbol. It's the gradient. We call it the gradient. And we will see why this is called the gradient if I can get that far into the lecture, which is simply a row vector of all the partial derivatives. I am using this, I'm calling the gradient a row vector. Other conventions could call it a column vector. You just have to adjust everything accordingly, right? But the basic concept must be clear from this. We're going to spend some time on derivatives today and on optimization, because this underlies a lot of the arithmetic that we're going to use. And in the following slides, I'm going to talk generally about this business of function optimization. I have a function. I want to find the lowest or the highest value of the function with respect to its argument. So in that case, I'm just using a generic notation where the argument of the function is going to be called x. The function value is going to be called f. This notation is not the notation we were using when we were defining our neural networks. Don't get confused. So I'm going to be flipping between x's and w's, and hopefully it still makes sense to you. So here's the problem of optimization. The general problem of function optimization is that you're given a function of this kind, or this kind, or this kind. And you want to find either the minimum or the maximum value of the function. Specifically, you will either need to want to find the minimum or maximum values, or the arguments at which the function takes its minimum or maximum value. Now, we've done this in school. For scalar functions of scalar variables, how do you compute the minimum? Anyone? I very helpfully put this on the slide, so I'm going to ask Sanan.
Find the derivative of the function and then solve it for 0.
And is that sufficient?
And then we have to check whether it's the minimum or maximum, so we take a second order derivative.
Second order.
If it's positive, it's minimum.
So this is high school stuff, right? I'm just bothering you because it's fun. But here's what it is. The slope of that function is going to be 0 at a minimum. So you can just check whether the slope is 0. But that's not sufficient. Because if you look at any function, if a function is going up, when the function rises, the slope is going to be positive. Then it hits a peak, the slope becomes 0. Beyond the peak, the slope is going to become negative, and so on. And again, at the minimum, as it falls, the slope is negative. It falls slower and slower, then it becomes flat. then a small change in the input causes no change in the output anymore, so the slope is 0, and then the slope becomes positive. So just stating that the slope is 0 is not sufficient. We also have, now, so if I plot the derivative over here, right until here the derivative is positive, so the derivative is going to be above the black line. In this region the derivative is negative, so the derivative is going to be below the black line. Here the derivative is 0, so you can see that the derivatives become 0 at both minimums and maxima, and minima and maxima, and so we have to check the double derivative, which is the slope of this red curve. And we will see that the double derivatives are negative at maxima and positive at minima. So the way we would actually solve for a maximum or a minimum is find the location x where the derivative is 0, and then if you want to find now a location where the derivative x is 0 and it's a minimum is what is called a turning point. Why is it a turning point? The function's literally turning. As you continue, the direction in which the function is changing is going to change. It will go from decreasing to increasing, or alternately it will go from increasing to decreasing. You guys at the back, oh, TAs, okay. So these are turning points, right? Now we're going to check if it's a turning point. We will find it if it's the turning point, and then we'll check the double derivative. If it's positive, then it's a minimum. If it's a negative, it's a maximum, right? It's not that simple, because functions can have maxima, they can have minima, but they can also have inflection points. An inflection point is where the function is moving along, maybe decreasing, maybe increasing, and then for a brief while it just rests. It doesn't change its value, and then continues in the same direction as before. So here the function is decreasing, and then it pauses briefly, and then continues to decrease. So if you looked at the derivative over here, what happens? The derivative is going to be maximum here. It's also the derivative is going to be 0 here. It's also going to be 0 at the inflection point, because at the inflection point the function sort of stopped changing for a very, very brief while. And then it's also 0 at the minimum. What about the double derivative? What would the behavior be? Anyone?
It will be 0, right?
The double derivative is going to be 0 at the inflection point. Because if you look at the derivative looks like so, right? So the derivative is 0 in all of these places. But at this location, the derivative went from being positive to negative, which means the second derivative is negative. Here it went from being negative to positive, so the second derivative is positive. Here, the second derivative went from being negative and continued to be negative. The derivative went from being negative and continued to be negative. So the second derivative is actually going to be 0. We have 3 kinds of, and so when you actually find, just saying that something takes its minimum value when the derivative is 0 is not sufficient. If the derivative is 0, you'd have to determine which of these 3 cases happened.
But in the previous slide, the slide says greater than equal to 0 at minima, less than equals to 0 at maxima, and 0 at inflection point. So it could be possible that it is 0 and it is a maximum?
It's yes, if it flattens out.
I see.
Right? That's the reason. At an inflection point it's guaranteed to be 0, but if the function goes like so and then flattens out, what's going to happen to the derivative, right? So now what about the functions of multiple variables? For functions of multiple variables, again, you have exactly the same behavior. When you're at a minimum is a turning point, meaning regardless of which direction you arrive at the minimum from, the value of the function is decreasing. And then as you go beyond the minimum, the value of the function will begin to increase. So minima are turning points. Here you have 2-dimensional inputs. It's a scalar output, that's a minimum. Here this is a minimum, that's actually a maximum, but that too is a turning point. So you just have to check whether it's a turning point, you'd have to check the derivative. And in the case of the derivative, what is the derivative for a function of multivariate inputs? We called it something just now. It was the gradient, right? So you'd have to check to make sure that every component of the gradient is 0. If only some components are 0 and others are not, is that a minimum? No, because there are some directions where the function continues to change. So every single component has to be a 0. And again, before we continue, a brief diversion again on what this magical term, the gradient, actually means. Now, we all know that the gradient is capturing some notion of the behavior, the response of the function to small changes, perturbations in the input. But is there something more than that? And to understand that, let's go back and look at what the gradient is. The gradient is just this multiplicative term. The gradient of a scalar function f of x of a multivariate input x is a multiplicative factor that gives us the change in f of x for tiny variations in x. This we've seen. If I write out the arithmetic, I just say f of x is a function of all of these variables. The way we defined the gradient was a row vector of partial derivatives. And so using this definition, my change in f of x is the gradient times the change in x. If I expand it out, you can check that this is exactly the same equation we had before. But what is this? This is a vector in a product. You have one vector, which is the gradient, the other vector, which is the perturbation in the input, right? And what do we know about vector inner products? So take a look at the board for now. Suppose I have two vectors, v, u, and another vector v, and both of them are unit length. What is the inner product going to be? Cos theta, right? This is theta, so u transpose v equals cos theta. This chalk is really horrible. Now, suppose v is not unit length. Then what is the inner product going to be? It's going to be the magnitude of v times cos theta, right? So consider this. Let's say I have this red vector as my, let me change this a bit. So if I have this as v, and let's say u is unit length, and this is theta, then v transpose u is simply going to be magnitude of v cos theta, right? Which is this length. Do you agree? Anybody have doubts there? This is high school stuff, right? You have to know. So now let's say that red vector is my vector v, and u is this line which is length 1. So both of them retain their length, but as I keep rotating u, what happens? When u is out here, the inner product is the length of this black line. When u is out here, the inner product is the length of this black line, right? So as u keeps rotating around, at which point is the inner product going to be largest? When the two are perfectly aligned, right? So now let's go back and look at our equation over here. The gradient is a property of the function. It has nothing to do with the increment in x. The gradient is a fixed vector. As I change the delta x, so let's say I fix the length of my increment, delta x. As delta x rotates, at which point is this inner product going to be maximum? When they are both exactly in the same direction. So what does this tell you about the gradient? It's the direction in which you must travel for the fastest increase in y. Correct? So the gradient of a function is simply the direction of the fastest increase in f of x. So here, for instance, if I have, this is the plane over which the function is defined. So if I'm over here, the gradient at this point, when I say the gradient at this point is in this direction, it means that if you walk in this direction, the function is going to increase fastest. There are many directions in which you can walk for the value of the function to increase. But the gradient is the one direction where the function is going to increase fastest. And conversely, if you walk opposite to the gradient, what is going to happen? The function is going to decrease fastest, right? And so that is negative gradient x. And of course, at the turning points, it doesn't matter which direction you walk in, the function's not going to increase, so the gradient is 0. Now here's another property of the gradient that we will use. I can always draw a level set for a function, which is to say I have the function, I slice it in some height, and if I sliced it, the slice is going to have a shape something like this. Say if I sliced it at this height, then the shape of the slice is going to be something like that. And you're guaranteed. Now remember, the gradient is a direction on the x-plane, correct? It has nothing to do with it's so because the gradient is it's a vector. It's telling you the direction of fastest increase, and this gradient is guaranteed to be at perpendicular to the equal value contour. So these are two properties that we will frequently use when we are actually optimizing functions. Now you can also define a second derivative. Just as we did for scalar functions, you can define a second derivative for functions of multivariate inputs, where each row is going to be the partial derivative with respect to two different variables. I won't get too much into this second derivative. It's called the Hessian, but the diagonals are dou square f over dou xi squared, and the ijth component is dou square f over dou xi dou xj. Easy enough, right? So returning to optimization. The optimum is going to be a turning point. The gradient is 0. Yes?
Sorry, in Hessian, in order to determine whether or not it's a maximum and minimum, are you just looking for whether or not the diagonals?
No. So I'm going to get to that. Okay. So if I want to decide if the optimum is a turning point, first the gradient is going to be 0. But that's not a sufficient condition. Correct? So what I really need to know is whether it's a maximum or a minimum. And now the Hessian is typically going to be a full matrix, but it's a symmetric matrix. And if you look at the eigenvectors of the Hessian, they're giving you the principal directions. Basically, it's aligning the function at that spot with respect to the axes. So if the function is curving up like so, then its step in x also affects the step in y. Meaning, if I just step along x, I'm going to get the kind of increase I get in the function could also have been obtained by corresponding increase by step along y. So if you want to decouple the x and y, you have to walk along the eigenvectors of the Hessian. We will see a little more of this in a subsequent lecture. So what we will do is to solve for where the gradient equals 0. Then you'd compute the Hessian at the candidate location, and the directions where the eigenvalues of the Hessian are positive are directions in which you have minimum. The directions in which the eigenvalues are negative are directions where you have maximum. And at intermediate locations, values, if it's 0, those are inflection points. Now, if you want a distinct minimum, this means that every single eigenvalue of the Hessian must be negative, must be positive. If you want a distinct maximum, every single eigenvalue of the Hessian must be negative. And if you have mixtures, then the function, the location where you are, has this property that in some directions, the function is has a local maximum, but if you walk in other directions, it's not a turning point. The function is a turning point in some directions and not in others. So it's not really either a minimum or a maximum. Right? So solving for this is kind of easy. Except it's really not, because it means that you need to have the value of the Hessian. You need to solve these complicated functions. Often it's simply not possible to solve this, set the gradient to 0 and solve for it, and you can't check the Hessian. So in this kind of situation, what we really need are iterative solutions. You begin with a guess for the optimal x, and you refine it iteratively until the correct value is obtained. So you'd say, start off by saying, I think this is the value at which the function is a minimum. Then you check the function, and how would you check if it's a minimum or not? You check if the gradient is 0 or the derivative is 0. If it's not, then you take a step in some direction and keep taking steps until hopefully you arrive at a location where the derivative is 0. And you can do this or until the function no longer decreases, which is different from saying the derivative is 0, right? So this is the scalar case. You'll be doing the same thing in the vector case. In the vector case, you're going to be walking in various directions till you arrive at the minimum. Questions? If I'm actually at any subpoint, and how do I determine whether it's a minimum or not? The simplest check is the gradient. So let's assume the gradient is not 0. After that, which direction do I walk in? And when I walk, I'm basically taking a step. How large must the step be? All of these are going to affect the solution that you get. So the iterative solution is something like this. You start at some point, find the direction in which to shift this point to decrease the error, and this can be found from the derivative of the function. So if it's a scalar function of a scalar variable, if the derivative is positive, it means that moving forward is going to increase the function. If I'm trying to find a minimum, that means I have to move backward. If the derivative is negative, it means moving forward is going to decrease the function. So if I want to decrease the function further, I want to move forward. So basically, if the derivative is positive, moving left decreases the error. If the derivative is negative, moving right decreases the error, where I'm defining left, right as is shown on the slide. And I'm not really sure what I did. Okay. So here is a trivial algorithm. I could start off with some x0, check the derivative, and while it's not 0, if you start off at a point where the derivative is 0, you're screwed, because you can't really know whether you're minimizing the function or maximizing the function. So where you really want to start off is where the derivative is not already 0. And at that point, I can check the sign of the derivative. If it's positive, I take a step backwards. If it's negative, I take a step forwards. So xk plus 1 is xk minus step, where step is a positive number, so I'm going backwards. Or if this derivative is negative, then xk plus 1 is xk plus step, where step again is a positive number. Now I can rewrite it differently. Instead of using an if clause, I can just multiply by the sign of the derivative, and it's the same thing. So if the derivative is positive, I'm taking a step backwards. If the derivative is negative, the sign of the derivative is negative, minus and minus is plus, I'm taking a step forwards. So this is still the same equation, same algorithm. Except now I can now merge the two and just say I directly use the derivative and use some step size, which is some unknown parameter. We'll deal with it later. So all of these are exactly the same logic that we began with, meaning if the derivative is positive, you walk against the direction of the derivative. Otherwise, you walk in the direction of the derivative, and you will hope to decrease the function. That was for a scalar function, but the same thing holds for multivariate functions. At each point, you can compute the gradient. We know the gradient is the direction of fastest increase. If you want to decrease the function, you want to decrease the value as rapidly as possible. So you're going to walk against the direction of the gradient, exactly opposite the direction of the gradient, which means that at each point from the current estimate, you're going to walk in the direction of minus of the gradient, and there's a step size. Now observe the transpose over here. Why do I need the transpose? Because the way I defined it, a gradient was a row vector, and I want to align it up with my vector x. So if you might see different variants of this algorithm where there's no transpose, that means they're thinking of the gradient as a column vector. But thinking of the gradient as a column vector will cause problems when we apply the chain rule. We'll see that later. So here is the overall algorithm. You start at some point, and keep walking against the direction of the gradient. When do you stop? You can check if the gradient is 0, or alternately, you can check if the change in function is smaller than some minimum threshold, meaning the function is beginning to taper off, so you can stop. Yes?
So when we do gradient descent, is our aim to reach a local minima or a global minimum?
The idea is here the intention is to get to a global minimum, but you're only guaranteed a local minimum.
Yeah.
So here's the overall algorithm. You initialize x while the function has not tapered off. Keep taking steps against the gradient. Easy enough, right? What kind of functions will this really work properly in, to address your question? If you have a nice bowl like this, then as you keep walking, you can hope to get to a solution. If I have some ugly, hideous function of this sort, if I start from here, I'm going to end up in a local minimum. If I start from here, I'm just going to end up at an inflection point. If the global minimum is here, so if I was starting from here, I end up at the global minimum. So where you start from is actually going to affect the solution, in addition to how big your steps are, and so on, right? So that was just a quick detour into optimization. Let's get back to our problem, which is, given a set of training instances, we defined an error, which is the average divergence over all of our training samples, and we want to minimize this with respect to the parameter w. This is function minimization, which means we can solve this using gradient descent, right? But to solve this using gradient descent, what was the first requirement? When I was talking about gradient descent, obviously, immediately it becomes obvious why I'm saying gradient descent, right? You're walking, descending against the gradient, the way we define the optimization. So this means I must be able to compute the gradient, right? That function error has to be differentiable. So every component of this has to be differentiable. That divergence has to be differentiable. If I'm looking to train a classifier, remember, when we were training using the perceptron rule, what were we trying to minimize? The number of misclassifications, right? Is the number of misclassifications a differentiable function? No, it's a discrete value, right? 1, 2, 3, 4, 5. It doesn't take intermediate values, which is why we had to soften our activation and redefine the manner in which we define the loss, the error, because otherwise this thing would not be differentiable. That was the distinction between Adeline and the perceptron rule, for those of you who are watching. And that's the entire class, right? Now, so the function f, the network, has to be differentiable with respect to every single parameter. The divergence has to be differentiable with respect to the function, because what is the argument of the divergence? The function itself. And if both of these are differentiable, then my overall error is differentiable, and now I can apply gradient descent to minimize the error. Correct? So these have established the basis for what we really want to do. But then we need the problem set up. I've just sort of defined all of these terms. There are many variables over here. What are the things I must define? What are the inputs? What are these desired outputs? What is this function f? What is this divergence div? Unless I actually define all of these carefully, I'm not really going to be able to complete the optimization. So let's go through all of these. Let's start with the function f itself, because this is the easiest one to define. We have a function, we have the parameters, and we all know what this function was supposed to be. This was just supposed to be a multilayer perceptron. The way we will define it, it's a directed network with inputs and outputs. There are no loops, which means that when I provide it any input, that is going to flow directly to the output without ever going back and revisiting any unit in the middle. So the input is generically going to be referred to as input units, although there are really no perceptrons at the input. It's just the input that you're providing. This is terminology that has been used for ages. I am not responsible for it, so don't ask me why it's used. But the input is going to be called a bunch of input units. The outputs, similarly, are going to be called output units, but here there are perceptrons computing the output. So fortunately, it's not an inappropriate terminology. And the intermediate stuff, we will call these hidden units. And we call them hidden because as far as the function is concerned, you can see the input, you can see the output. What happened in between is not of direct relevance to you, and it's not directly observed. So those are hidden units. Now the individual units themselves are going to be what we've seen before. Each unit gets a bunch of inputs from somewhere, which could be the outputs of other units. You're going to compute an affine combination of all of its inputs, and then that goes through some activation. So we're going to assume that this activation is differentiable, or at least semi-differentiable. By semi-differentiable, if you know something like this red line over here, this red curve over here is not differentiable everywhere. There is one point where it doesn't have a derivative. I can nevertheless define something very similar to a derivative, which is a subgradient. So we're going to assume that functions are of this kind. And although this is what we will assume, unless otherwise specified, which is to say that any particular perceptron has weights and a bias as its parameters, more generally keep in mind that you can use any differentiable function as a perceptron, and the entire arithmetic, everything that we're talking about, the business of optimization, the business of trying to approximate one function using a network, everything holds, right? And standard activations, here are some typical activations. The one that we've seen so far are the threshold activations, where you have a threshold function, the sine function operating on the affine combination of inputs. But then you can have others. One of the most common is the sigmoid. We've seen this already, which is 1 over 1 plus e raised to minus z, where z is the input to the activation. Z again is the affine combination of inputs to the unit, right? So, and the derivative of this one, if you work it out, is just going to be f of z times 1 minus f of z. I won't waste time on this on the board. It's very trivial to derive. Here's another one, which looks a whole lot like a sigmoid, but it's kind of shifted down. Now, the nice thing about this is that it doesn't go from 0 to 1. It goes from minus 1 to 1. And that too, that's a variant on the basic sigmoid, which gives you a certain degree of flexibility. For instance, if you're trying to perform a classification and your class labels are not 0 and 1, but minus 1 and 1, then the tan H is probably more appropriate. There are other reasons to be using the activation, the tan H activation. But here's another one that's popular. And we will actually see some cases of neural networks where this is way more appropriate than this guy for reasons besides just the minus 1, 1 shift. And the derivative of the tan H is 1 minus f squared z. Then you also have these two. The red line is what is called the rectified linear unit, or the ReLU. You must have encountered this in your homework already, which is 0 for negative inputs and the same as the input for positive inputs. And its softer version, which is the soft plus, which is log of 1 plus e raised to z. Now look at what happens over here. If z is a large negative number, e raised to a large negative number is 0, right? So the argument ends up becoming just 1, and what is log of 1? 0. On the other hand, if z is a large positive number, what is e raised to z? Some large positive number. Adding 1 to it makes no difference at all. So this log of 1 plus e raised to z simply becomes z. And so it's a nice smooth version of the rectified linear unit. So those two are used, and the derivative for that is given here. Now, the derivative for the rectified linear unit, I've put a star against it because it's not really clearly, there's no derivative defined at 0. We will use this, generally use this convention. There are any number of subgradients you can define at 0. And you can either set the subgradient to 1 or 0. Using 1 makes more sense in most cases. Now, this was a question that actually came up in the on Piazza. I've been thinking of every unit as a unit unto itself. Every single, we are really speaking of networks of perceptrons. Meaning I have this bucket full of perceptrons, I pull them out, I connect them up with wires. So every perceptron was an individual unit operating all by itself. It got a bunch of inputs, computed an affine combination, and then transformed it using a some kind of a differentiable activation. But another way of thinking about it is saying, I have this big block which gets a bunch of inputs and produces a bunch of outputs. So this is a function where the output is a vector and the input is a vector. And that too is a perfectly appropriate way of thinking about it. So in this now, what is the basic difference between the two? So how do I distinguish between these two cases? One can argue that they are basically two cases, two sides of the same. They're both basically the same definition. From our perspective, they are not. And let me explain why. So let's say I have these 4 inputs. And let's say at the next layer, maybe I have 3 connections, 3 perceptrons. So I have all of these. Every edge here has a weight associated with it. So let's say I fix these inputs, right? These are all fixed. I give you some input over here. If I change this weight, which output changes? Just this one weight output changes, right? Because this weight is not affecting these guys. So here I can write yi equals some f of, let me call these y's, let me call these x's, x1 through x4. fi of x1 through x4. And each of them is a different function. Each of them has a different set of weights. Or more generally, I can say f of x1 through x4, comma, w1, 1j, j equals 1 to 4. So because these are the weights, correct? Now, let me throw a different function. Here, I'm going to define a different function where it's the same setup. I have 4 inputs, but now I have a box and I have 3 outputs. And maybe I even have a peculiar bunch of connections like this. But the situation here is that if I change this weight, it's not just this output that changes. Every single output changes. So here I cannot write it in the scalar form. I'd have to say this is x, this is y, and I'm going to say y equals f of x, where x is a vector and y is a vector. The two are different cases. Do you see the distinction between the two? And if you don't see the distinction, let's see look at an example. The most common example here is the Softmax. So the Softmax, I have a bunch of inputs x. I would compute as many z's as the number of outputs I want. Each of them is a different affine combination of the inputs. And then to compute the output, I'm just going to exponentiate the corresponding z, right? But with one change. I'm going to normalize these outputs so that they sum to 1. So now the output looks like a probability vector, all positive numbers, and they sum to 1. But then what happens? Say I change this weight. Let's say I increase that weight, or let's forget about the weight even. Let's say I increase the z. I increase zl. What will happen to the outputs? All of the y's will change, right? This y is going to increase. The rest of them are going to decrease to compensate. So in other words, if I change this little weight, it's no longer this term alone that changes. The entire output changes. So this is what I will call a vector activation. And the parameters, again, are the weights and biases. So you see the distinction between the two, right? And here's another case. Instead of having this weighted combination, I can have something that's multiplicative, where each output is a product of all of these inputs raised to a different value. So all of the dotted lines are actually going to have a weight associated with it, an alpha term, except the inputs are now raised to alpha and they're all multiplied. So this is like a multiplicative combination of inputs. But this too is a vector activation, and the same rule applies, right? And finally, before I continue, we're going to assume a layered network for simplicity, which means that we have an architecture of this kind, which can be separated into virtual layers. Each layer only communicates with the immediately subsequent layer. So we don't have connections going from here to here. The most generic case would allow those connections, but just for ease of explanation, I'm going to use this kind of architecture. So we will call this the input layer. These input units together form an input layer. The output units together form the output layer. And remember, there's no such thing as an input unit. The input units are just the inputs. So you have the input layer, the output layer, and in between, all the hidden units are arranged in hidden layers. Questions, anyone? Any question, Piazza? None? Okay. And of course, in a layered network, each layer can now actually be viewed as a vector activation of the trivial kind, where changing one input changes only one output. Right? So it's like having many independent entries can be thought as a trivial vector activation. So notation, I'm going to call the inputs x. D is the dimensionality, which is the number of units in any layer. I'm going to have this wij superscript. So wij is the weight from the ith unit in this layer to the jth unit in this layer, and the superscript represents the layer number. So wij k is the connection between the ith unit of the k minus 1th layer and the jth unit of the kth layer. I'm going to have these y's, so yi superscript j is k is the output of the ith unit in the kth layer. The weights, the biases are using the same notation as the weights. I just say bj superscript k, it's the bias assigned to the jth unit of the kth layer. So the notations, hopefully the notation's not confusing. It's fairly straightforward. So we've defined f. What about these inputs? How do we define these inputs and outputs? So I'm going to, so let's think of it from a more programmatic perspective. I have many inputs of this kind. Each input is actually a vector. It's a many component vector. And the outputs may be either scalars or the desired outputs, the target outputs, may either be scalars or vectors. We will see the difference between the two in a minute. And I'm also going to say yn, which is the output of the final layer of the network. So maybe I missed this when I was talking about this, talking about it here. Let me see if I have it. I'm stupid. It's not here. Right. Come on. Okay. I'm going back too much. So the output of the final layer of the network, which I will represent using an uppercase y, is also going to be a vector. So this is the response of the network to this input, and this is the desired response for that input. And yeah.
So Dn is the output in the hidden layer, right?
Which one?
D.
No, D is the desired output. Remember, these are the input-output pairs that we're trying to map. So we're learning a network to learn this relation from x to d. But the actual output of the network is y. So we're going to call all outputs y's. The final layer is just called an uppercase y. This was the notation I had introduced right here, right? Every hidden layer, the outputs of the hidden layers are also all y. Okay, d is the desired output. Okay. And sometimes, I'm not going to use this additional notation, just index n, because it gets very confusing. So now, what about the input? The input is just a vector of numbers. Like if I'm analyzing pictures, it could be a vector of pixel values. Or if I'm analyzing speech, it could be a vector of speech features. Or if I'm analyzing text, it could be a vector of real valued numbers representing text. We will see how these numbers could be derived later. So, and other real valued vectors. What's more interesting is how we represent the output, because really we are performing, if you're performing regression, the output is just a real number, easy. If you're performing classification, you're going into an abstract set. Is this a dog or is this a cat? How do you assign numbers to this sort of thing? So for real valued outputs, these are just real valued variables, no big deal. But if the output is binary, let's say, is this a cat or is this not? Then you're going to have to convert their two numbers, which means I'm going to assign the number 1 to cat and 0 to not cat. And this perceptron, this output unit is expected to have a binary output. The output is either 0 or 1. Now, in reality, what you won't actually get, you won't actually be using a threshold unit. You'd be using a sigmoid. Everything is differentiable, right? So that goes from 0 to 1. So you would view this as the probability of y equals 1 given the input. And we saw this again, why this makes sense in the last class. So this is going to be, in our case, what is the probability that the picture that we just saw is a cat, for instance. Now, if I have vector outputs, meaning suppose I want to decide if I'm performing multi-class classification, like deciding if the picture is that of a cat, a dog, a camel, a hat, or a flower. Now, I will arrange all of my classes in some pre-specified format. It's pre-specified order, like cat, dog, camel, hat, flower. And now each output is going to be, this has 5 components. So each output is now going to be a 5-component vector. And the desired output is going to be what we call a one-hot vector. Why is it one-hot? There's going to be a single entry which has the value 1. All the other values are going to be 0. So here, this one-hot vector has 1 in the first component and 0 everywhere else, which means I'm assigning a 1 to cat and 0 to the others. This means I'm representing the class cat. So also, this has a 1 in the second component, and everything else is 0. And the second component was assigned to dog, so I'm representing the class dog. If I have a 1 in the third component in this example, I'm representing the class camel, and so on. This is a one-hot vector, and for an input of any class, we will have a 5-dimensional vector output with 4 zeros and a single position, 1, and the position for that class. This is a one-hot vector. What will the network output actually be? So that's if I give you training inputs, I'm going to give you some vector x, and I'm going to give you a desired output d, which is a one-hot vector. Because I want to say, I want the network to see this picture and say it's a cat. So the desired output is going to be 0, 1, 0, 0, 0. The actual output of the network, remember, we have differentiable functions. It's not going to be that straightforward. So the actual output must ideally be a 1 here and 0 everywhere else. More realistically, it's going to be a probability vector where the components sum to 1. So in the multi-class classification, what is this probability vector going to be? We'd be using the softmax that we just saw. I could just use a softmax layer, and we already saw that the softmax layer is going to give you a set of probability-ish values. And we are going to try to learn this network so that that actually reasonably accurately represents the a posteriori probability of the class given the input for each of the classes. So the ith output of the softmax in the final layer is going to be the probability that the input belongs to the ith class, right, given the input. So here's a typical problem statement. You'll be given a bunch of data, training data instances like images of digits along with information about which digit represents, which image represents which digit. For binary recognition, you'd have tasks like is this a 2 or not. For multi-classes, it's going to be which digit is it? Or even is it a digit in the first place? So if you were trying to perform binary recognition, does this image represent the digit 2 or not? The input-output pairs are going to be your pictures, these black patches, and the labels would be what is shown in red. Yes, this is a 2. No, this is not a 2. So 5 is this is clearly not an image of 2, so the label is 0. This is an instance of 2, so the label is 1. This is not a 2, so this is 0. This is a 2, so the label is 1, and so on. And you'd have a network of this kind, where the output is going to be a sigmoid going from 0 to 1. If you had a multi-class classification where you're trying to determine assign a class, the actual value of the digit to the input, then the label is actually going to be the value of the class itself. Of course, when you convert it for the purpose of the network, this number 5 is going to be, if I'm recognizing 9 digits or 10 digits, that number 5 is going to be a one-hot 10-dimensional vector with a 1 in the 5th position and 0 everywhere else. Right? So you're going to have a bunch of these training examples, and now our problem is to learn all the weights of the network to do the desired job. We've defined input-output pairs. We've defined the function. We've defined one more term that remains to be defined, which is this divergence. What is this dive? The divergence quantifies the difference between the actual output of the network and the output that you want to see, right? Now, if the output of the target output of the network is real, do you mind shutting the laptop? Do you mind shutting the laptop? Yes, thank you. So if the target output of the network is real valued, then I can just define the standard Euclidean distance or a scaled version. So here's a y minus d squared norm as the squared Euclidean distance between the target output, which is a vector, d is a vector, remember, and the actual output y, which is also a vector. We toss in this factor half just for the sake of convenience. You don't need to. So that's going to be half of sum over all the components of the squared difference between the actual output of the network and the desired output of the network. And why the half? Because if you differentiate it with respect to any given yi, it's simply going to be y minus d, which is just the difference, the error. And so specifically because of this, because the derivative is simply the actual difference, the error, the entire process of training using gradient descent is called error backpropagation, because we are going to be using the chain rule to compute the derivatives of the error with respect to intermediate values, and it turns out it just ends up doing a lot of multiplies and additions of this basic error. So it's called error backpropagation. But anyway, that's just an aside. So for the L2, for real valued vectors, it's very clear how we define the divergence. If you're performing binary classification, then we need some kind of a divergence metric that tells you how much your network is off. So if the network, let's say you want a 1, 0, and the network outputs a 0, 1, how much is it off? If the network outputs a 1, 0, how much is it off? If the network outputs a half and half, how much is it off? You could use the L2 divergence again. It turns out it's not very effective. So we actually use something called the cross entropy in this case, which is this one. So D is the desired output, which is either 0 or 1. Y is the actual output. And it's going to be minus of d log y minus 1 minus d log 1 minus y. Now, where does this actually come from? What would happen if d is exactly equal to y, or y is exactly equal to d? So if y is exactly equal to d, then if d is 0, right, it's going to be 1. This is 1 times log 1. Log 1 is a 0. So this term goes away. This is 0 log 0. That becomes 0. If d is 1, this becomes 1 times log 0, which goes away. This is 1 minus d becomes a 0. This becomes a 0 log 0. It goes away. So when the output and the input and the desired output and the target output are the same, this value becomes 0. And on the other extreme, if d and y are exactly opposite one another, then what happens? So if d is 1 and y is 0, you get minus d log y. And log y log 0 is minus infinity, right? So minus and minus become plus. That's why you need the minus. So you're infinitely penalizing something that's perfectly wrong all the time. And you're not penalizing something that's perfectly right. So, and of course, if you compute the derivative of this guy, it's going to be, with respect to y, it's going to be minus d over log y plus 1 minus d over 1 minus y. But d is either 0 or 1, correct? So when d is 1, only the minus 1 over y term remains. When d is 0, 1 over 1 minus y remains. So this is the derivative. For multi-class classification, we have a generalization of this basic principle, which is that you'd be summing over all the classes, and you'd be taking minus d log y. The same concept still holds. If d and y are the same, this is going to be 0. On the other hand, if it's performing perfect misclassification, if it's assigning zero valued probability to the correct class, it doesn't matter what it's doing for the other classes, it's being infinitely penalized, right? And if you take the derivative, what are you going to get? So you would have, this is, so you have d and you have y. This is a horrible chalk. So d is going to be something like 0, 0, 1, 0, 0. And you have some y1, y2, y3, and so on. So the only one that you have to worry about is this term, because this is the only class for which the d value is 1 when you're computing the derivative. And so this is going to be just the derivative. And for that class, derivative of log y is 1 over y, right? And that's going to be minus of 1 over yc for the cth component, where c is the true class of the instance. For every other class, the derivative with any other y is simply going to be 0 because the corresponding d term is 0. So we've defined questions. Yeah.
So here we're talking about hard classification, right? So what about soft classification?
So this d is the target output. Y is the actual output. Y is going to be a bunch of probabilities, always. Right? You want, ideally you want the network to be unequivocal when it produces, when it operates on your data. If I give it a picture of a cat and I know it's a cat, and I'm not going to tell the network, I'm half sure it's a cat, right? In principle, D could also be probabilities. Nothing changes. The same principle holds. The same principle holds. The derivatives would change. These derivatives are defined for definitive class labels. That's all. So we've defined the whole thing, right? Every single component of this problem. Now, what is the key piece over here? The key piece now is the total error. If the error on the ith instance is defined by this divergence, the total error is the average of these divergences over all the training instances. And that is what you'd stick into the gradient descent. The function f is the average error. And the way you would do it is basically iteratively walk against the gradient of this average error with respect to all of the parameters in the network. And if I explicitly write it out, you're going to go over, actually let me do this on my actual on the parameters of the network. I have many layers. For every layer I have several connections. So I'm going to iteratively go over my data and keep updating my weights against the derivative of the error with respect to that parameter. This is the partial derivative of the error with respect to the parameter. This is exactly going to be gradient descent. The one key piece over here that we will have to come back to later is this term eta. Eta is the step size. And if you're actually using gradient descent, observe that this step size is common for all components, because the step size tells you what is the length of the step you're taking against the gradient. And that's going to be the same for every single component, right? That's going to come back and bite us. And so that's the step size, which is common for all components. The key piece is what is the derivative of this error with respect to any given parameter. And if I look at it closely, that error is the average divergence over all the training instances. The averaging operation is linear. So if I want to take the derivative of the error with respect to any weight, I can actually take the derivative. The derivative moves in, so it's the average of the derivative of the divergences for individual training instances with respect to the parameter, right? And so this is the term that we need to be able to compute in order to train our network. Now, ideally, I would have been at this point half an hour earlier, but between my delay and various other things, we haven't got here. But I'm going to just quickly give you, in the next 5 minutes, a calculus refresher. You're going to have to wait with me for a few more minutes beyond the end of the class. So for any differentiable function with derivative dy over dx, we said that this must hold. This is, in fact, the definition of the derivative, correct? So for, let's say I have a function y of many variables, then we also saw that this must hold. This again was the definition of the derivative, right? Now the chain rule, how can you actually check the chain rule? Let's say I have function y equals f of g of x. Then dy over dx is dy over dg of x times dgf of x over dx. This is what you've learned in school. Let's see if this actually can be worked out using the chain rule, using the basic definition of derivatives. So if the definition of derivatives holds, this must hold, right? Delta y must be derivative times delta x. So first, let me start off by saying z equals g of x. So that is y equals f of z, correct? If I say z equals g of x. But from this relation, I get delta z equals dg of x over d of x times delta x. So this relation I can plug in. Since y is f of z, delta y is dy over dz times delta z, again by definition. But delta z is this guy. So I can plug this term here instead of delta z. And that's going to give dy over dz times dg over dx times dx. So this term is what multiplies delta of x to give me delta of y. So the overall derivative of y with respect to x is this guy, dy over dz, which is simply g of x, times dg of x over dx. Does that make sense to you guys? Right? Simply sort of showing you how the chain rule actually operates. And now it's important to understand this and what's happening. In the last portion of the class, in the 3 minutes after we run over, I'm going to give you the most important component of this class, which kind of ensures that you stay here, because if you go away, you won't understand anything else. So now let me think of another function. Y is a function of many g's, right? And each of these g's is in turn a function of x. The claim here is the derivative of y with respect to x is dy over dg1 times dg1 over dx plus dy over dg, this should have been g2. I keep making this mistake. Brian, one of the TAs, can you note down the error on the slide number 102? Right. So plus dy over dg2 times dg2 over dx all the way up to dgm, right? Can I verify this? How would I verify this? To verify this, what I really must verify is that this relationship holds. And so first, let me say any zi equals gi of x, just by definition. So using this, you have y equals f of z1, z2, z3, z4, and so on. And we've already seen that this relationship holds in the previous slide, right? And we also have dz, based on this definition, is dgi over dx times delta x. So plugging this relation into these guys, you're going to see delta y is dy over dz times dg over dx times delta x plus dy over dz2 times dg2 over dx times delta x. I can group things up, and the term within the parenthesis is exactly what you've got over here. So this relationship holds. See.
What was the error in the slide?
Which one? G2. Right. So you see this. Now this is something that you actually seen in class earlier, but I'm just showing you how this is derived, and it's actually very trivial to see how this works out. But here's a better way of looking at it. And this is very important, right? So my function g, my input g affects each of these functions. My input x affects each of these functions g. Each of these functions g in turn affects x. So although they seem superficially coupled, right? If I change g1, obviously g2 must also be changing, because the corresponding x must have changed g2. So somehow the whole thing seems very tangled. It really is not. When you go into the infinitesimal scale, they get nicely untangled. This is the correct way to look at it. A change of x affects every one of these guys. A change in any of these guys is going to affect y. So when I think of how much does a small change in x affect a small change in, affect y, a small change in x results in a small change in g, which results in a small change in y. A small change in x affects a small change in g2, which results in a small change in y. And all of these contributions are additive. And it's very important. This is basic. This is a basic relationship. When you get really close, very close to a differentiable function, basically the contributions of every argument are additive because the relationship becomes planar. It's very trivial to prove. We actually did prove this half an hour ago, but this is, maybe you didn't register. And so this particular aspect is something that we're going to use repeatedly in the next several lectures. Basically, if I have a function of this kind, the way you should think about it is in this form. This is what I will call a dependency net diagram. And based on these, you can actually compute the derivative of y with respect to x by adding the contributions of every connection between y and x. And the contribution of any given connection can locally be computed using the chain rule. Right? So I'll stop right here and we'll pick up on Wednesday.